Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on the sigma notation and partial sums. Today, we will be learning how to find the nth partial sum of a sequence and how to compute the partial sums of progressions using sigma notation. Are you ready, students? Given the sequence AN, we will learn to find the sum of the first n terms called the partial sum, which is denoted by Sn. Therefore, if A1, A2, A3, and so on to AN are the terms of a sequence, we must express the following. S1 is the first term of the sequence. S2 is the sum of the first two terms of the sequence. S3 is the sum of the first three terms of the sequence. This pattern continues until Sn is the sum of the first n terms of the sequence. It is time for our first activity, students. Given the general term An equals 2n plus 7, find S10. I will see you in a few moments.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. The first 10 terms given by this sequence are 9, 11, 13, 15, 17, 19, 21, 23, 25, and 27. The sum of these 10 numbers is 180. Therefore, S10 equals 180. When we have a formula for the general term of a sequence, we may express the sum of the first n terms of the sequence in a more compact form. The Greek letter sigma is a special notation for sums. In this notation, I is called the index of the summation, or simply the index. 1 is the lower limit and n is the upper limit. If an is a sequence, the sum of the first n terms of the sequence, denoted by Sn, is called the partial sum of the sequence. Now, let us see how we may use this notation to help us to find the partial sum of an arithmetic sequence. We begin by examining a special arithmetic sequence. 1, 2, 3, 4, and so on to n. The associated sum of this sequence is Sn. Let us try to find S100. Luckily, there is a simple procedure that does not involve the tiresome addition of all the integers between 1 and 100. First, we express S100 as an equation. Then, we write the sum in reverse order. Notice that when we add each pair of terms together, denoted by 2s, we are left with the same sum, 101. 2s 100 equals the product of 100 multiplied by 101. Therefore, S100 equals half times 100 times 101. This equals 5,050, which is our answer. We can generalize this approach to derive this formula. The sum of the first n positive integers is given by Sn equals 1 and 2 and 3 and n, which equals n over 2 times the sum of n and 1. Try applying this formula for yourself, students. Find the sum of the first 50 natural numbers.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again. S50 equals 50 over 2 times 50 plus 1. This can be simplified into 25 times 51, which equals 1,275. Well done. This formula can be used to prove a theorem regarding arithmetic sequences. The sum Sn of the first n terms of an arithmetic sequence with first term a1 and common difference d is Sn equals sigma ak with index k, upper limit n, and lower limit 1. This equals n over 2 times 2a1 plus the difference of n minus 1 times d. We can also find a formula to let us do the same with geometric sequences. Let Gn be a geometric sequence with common ratio r. Then the sum of the first n terms, Sn, is given by Sn equals Ng1 if r equals 1. If r does not equal 1, Sn equals G1 times 1 minus r to the power of n over 1 minus r. This can be expressed as G1 times r to the power of n minus 1 over r minus 1. We have time for a last activity, students. The population of Addis Ababa is about 3.4 million people. If the city's population grows by 2% per year, what will the population be in 5 years? You may get started right away.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
How did you do with this problem, students? Let Pn be the population of the city after n years. Then P1 equals 3.4 million times 1.02. P2 equals 3.4 million times 1.02 squared. Therefore, we can see that Pn equals 3.4 million times 1.02 to the power of n. Our answer must be equal to 3.4 million times 1.02 to the power of 5. This is equal to about 3,753,875 people. Great job! That is all the time we have for today. Until next lesson, thank you, teacher. Thank you, students.